So what are graph convolutional networks? Graph convolutional networks look to embed graph information using neural networks. They take a graph representation, like an adjacency matrix, and use that to do deep learning on the graph. This is traditionally a hard problem for large graphs because of their complexity, but this technique works well to maintain node similarity, features, and graph topology. First, a little background on machine learning and neural networks. Neural networks are not new technology, and many people are familiar with how they work, so I'll be brief in my overview of them. Basically, these models aim to predict an outcome based on a set of examples. They look at the examples and learn from them by using some complex math and then attempt to minimize the amount of error they have when trying to predict new results. There are two primary types of machine learning problems. They are classification and regression. Classification is the set of problems that looks to give a specific label to an unseen data point, where regression problems look to produce a value for that point. Machine learning problems can also be generalized into two other categories, which are supervised and unsupervised learning. Supervised learning uses class labels to learn features associated with those labels and is used for classification generally. GCNs use unsupervised learning for the most part, and they learn from the graph structure without putting any labels on nodes or features. Getting back to GCNs, let's dive into more detail about what they are and what they do. GCNs can be summed up in a three-step process, and while there are some variations, this is the general idea. First, a particular node is generalized into a vector of features that represent that node. This is called a singular node embedding. Simply, a defined embedding function is used to map nodes in a high-dimensional space to a lower-dimensional space. Then at each step of the neural network, this vector is generalized by including information about the neighboring nodes. This allows for more than just the information of the primary node to be represented in the network. Then, after the input to the network has been computed, normal neural network computations produce an output subject to a nonlinear activation function. Then the result is evaluated with a loss function, and the error is back-propagated to tune the internal weights in the system so that it will be more accurate in the future. This is the learning component of the neural network. There are many other parameters that one can modify, such as learning rate and the number of hidden layers to get better results. Now, let's talk about this three-step process in a little bit more detail. First, a set of training nodes should be chosen from the graph so that the model can learn from them. It should be a completely connected component, and the model will learn from the nodes and the interactions between them to generalize trends to the rest of the graph. Now here comes the cool part. At each step of the network training process, neighborhood aggregation is performed. There are multiple ways to represent neighborhoods in graphs that appear in the literature. The most simple would be to take a weighted average of the feature vectors of the surrounding nodes with the central node in the graph. There are other ways to do this using random walks and other mechanisms which I will get into later. At the first level of the network, only the central node is used for learning. Then for each hidden layer in the network, more neighboring nodes are considered, so that at hidden level k in the neural network, the model is learning about nodes k hops away from the central node. The network is then optimized at each step using stochastic gradient descent or your favorite network optimization method to minimize the error in the final layer. Remember, the goal is to produce a model that has almost no error by the end of the training, as it should be able to correctly explain unseen data. The idea is that if it learns correctly from the training data, it will be able to generalize the trends that it's seen to predict the features and the arrangements of unseen nodes in the future. That's what gives neural networks such a strong property to extrapolate to unseen data. One cool variant on neighborhood aggregation is called an attention mechanism. The goal of attention mechanisms is to compute the node neighborhoods by weighting the neighboring nodes differently. Certain nodes will quote-unquote pay attention to each other or a different node and store more information about that node in its own encoding than the rest of its neighbors. For instance, the node in the center of the picture stores information about more of the peripheral nodes, whereas the smaller nodes don't store as much information about the nodes in their surrounding areas. This allows for a specification of node importance in its surrounding neighborhoods. Additionally, it is computationally efficient and memory efficient too. So this sort of method would be more scalable than just normal neighborhood aggregation using averaging of the weights of the neighborhood vectors. Now, I move on to a cool development in the field of GCNs. Recent work has shown that removing the nonlinearities in the GCNs produces accurate results, but with much less time used to train the models. This approach is called simplified graph convolutional networks, and it is both faster by 2 orders of magnitude to the next best GCN, and in some cases more accurate than the traditional GCN models. In a GCN, node representations are updated in the 3 steps I've explained in this presentation. When the model learns, it applies a nonlinear activation function to the combination of weights and features to see if a node is activated in the next layer. Because at layer k in the neural network, the features are averaged from nodes up to k hops away, the deeper the network, the more information about the local graph structure is used to learn. Then, it benefits the network to have deep layers because it can learn from more of a generalized neighborhood. To linearize the GCN, the nonlinear activation function is removed and replaced with a softmax function, which causes the resulting layer to be a linear transformation of the layer beneath. This approach is somewhat simpler than the methods used normally because it requires less computational power, while being a little bit more naive. The result of the research shows that this methodology, with a few other tweaks like adding dropout layers, produces very robust models. The resulting SGN can perform the same extrapolations that GCNs can, with a drastic improvement with respect to training time. This approach could make using GCNs in the future much more feasible because of the improved learning time. As the figure at the bottom shows, SGNs are much more efficient and produce the same level of accuracy as their GCN counterparts. Now that you understand how graph convolutional networks work and what they can be used for, you can understand that they are very promising new technology that can be used to do some amazing things in the future. If you have any questions, you may ask them now as the presentation is over.